Greetings, detectives. Mrs. McKay here, and we are ready to start on case 5. And case 5 is called water play, and the main reason is because a lot of the activities that we're going to do in class and a lot of the work that you'll be doing in your practice is going to be related to water features. And mainly what we'll be focusing on this entire case is looking at different functions and looking at the key features or the big characteristics, the main characteristics of different functions. So we're going to start with just a little intro today, and it's mostly going to be a review for you if you have finished case 4 and you finished it and closed it with confidence. So our learning target today is I can describe, so go ahead and write the word describe right here. I can describe a function and identify key features. And then I'm going to give you a list of some of them that we'll be able to do. I can describe a function and identify key features such as increasing, decreasing, positive or negative, continuous, discrete, linear, and exponential. So let's go ahead and go through each of these, and I'm actually going to add a few more as well that you need to be able to do. So let's go ahead and we need to make sure we understand all of this vocabulary. So the first thing is linear or exponential. And we've just spent an entire case working on linear functions and exponential functions. But just to make sure that you remember, a linear function has a constant rate of change. And if you graphed it, go ahead and draw a graph here. If you graphed it, it would make a straight line with a slope. So let's go ahead and make our so that's a linear function. Now, a exponential function has a constant change factor or a ratio. It's a change factor. And if you remember, we'll go up here, we'll say this is y equals mx plus b is one of the ways that we represent a linear function. And for an exponential, we represent it as y equals a to the x power. And there might be other things in front of it as well, or r to the x power if we want to call it our ratio. Okay, that's an x up there. So the idea is that our x is the exponent and that we have a starting point, and then we also have a ratio that we are, or a factor that we are constantly multiplying our starting point by. And typically, an exponential function has a curve that tends to go straight up. Let's see if I can make that happen, okay? All right, so we know how to recognize linear and exponential functions, and hopefully you know how to recognize them also when you're looking at the equation and if you're looking at a table, because the table can also tell us if we look at the differences between each y value compare over the x value. If we see that it's a constant rate of change, then we know it's linear. If we see that it's multiplying, that there's a change factor from one to the next, then we know that it is exponential. All right. Increasing or decreasing. Now, the main idea with this is that you want to read a graph the same way that you read a book, from left to right, okay? From left to right. The other thing that's important is that you want to look at the y values. Look at y values. So let me give you an example. So an increasing graph will look something like this. Right? From left to right, my line is getting bigger, or my y values are increasing, okay? Whereas a decreasing will look like this. From left to right, my y values are going down. They're decreasing. So you can also think of when you're looking at a line that you climb up a hill, you slide down a hill, okay? Now, with an exponential function, it's the same way. You want to look at increasing from left to right. Oops, let me go back to my pen. Increasing from left to right, my y values are increasing. They're going up, right? As I move from left to right, my y values are going up. And decreasing as I move from left to right, my y values are getting smaller. So increasing or decreasing, pretty simple. Now, the next thing that we're going to talk about are positive and negative. And we have talked about positive and negative slopes, but we've never talked about positive and negative functions. And really, when we define a function as positive, we're not defining the entire function. We define a part of the function as positive or a part of the function as negative. So let me show you what I mean. And all positive or negative means is if well, that is terrible looking, but that's all right. Let me draw my linear equation again. Okay, and then let's also draw our exponential function. All right, now what we're going to look at is we're going to say where is, where are the y values positive on our linear function? Where are the y values positive? Well, they're positive from here to here, right? The y values are positive from here to here. So they are positive when, they're positive, I'll just put a little positive sign, when x is, and we'll just say that's a -1 right there, all right? When x is greater than -1. So they're positive when x is greater than -1, okay? And they are negative, the y values are negative when x is less than -1. Does that make sense? So they're positive when x is greater than -1. So when x is 0, the y value is 1. When x is 1, the y value is almost 2. Okay, so the y values are positive when x is greater than -1. But the y values are negative when x is less than -1. When x is less than -1. So the thing that you want to think about is when are the y values negative, negative or positive, okay? All right, when are the y values negative or positive in terms of x? Okay, now let's look at this exponential one. The exponential one, when is the y value positive? Well, according to my graph, it's always positive, isn't it? It's always positive, especially if I have it start maybe right here. I'm going to have it start right there, and then it's going to come down like that. Okay, so it's always positive, isn't it? So because this one, it will never, ever, ever reach 0. Y will never, ever, it will get very, very close, but it will never reach 0. So it's positive when x is greater than 0, okay? And it's negative never. All right, so it's never negative. The y value is never negative, okay? But it will be positive as long as x is greater than 0. My graph is actually starting right up here where x is 0, and every other point after that is when y is positive. So that's positive and negative. You just have to really think about looking at the y values and when is it positive, when is it negative, based on the x, and you write an inequality based on the x. All right. Continuous or discrete, we've done a lot with continuous and discrete. Probably the hardest thing is to notice when you're looking at, if you're looking at a table, you don't know if it's continuous or discrete because you don't know if you have all of the values, and now you don't know if all the values are connected. When you're reading a problem, you have to really think about what does the problem mean and how you would decide whether, when you graphed that, if that would be individual points or if it would be a continuous one. So the easiest way, of course, is when you're looking at a graph, right? So you have a graph, and if you see that all of your points are connected, then you know that it is continuous. But in our example in class today, I was asking you, yesterday, I was asking you questions about when the water was being taken out of the pool with the bucket. Was it a continuous action or was it a discrete action? And in that situation, it would have been discrete, right? The water wasn't continually coming out. She would take a bucket, she would remove the water, and then the water level would stay the same, and then she would go back and she would take another bucket out and the water level would go down. So that would be an example of a discrete function. And so it might look something like this, where she's taking buckets out, but then when she started using the hose, maybe right here is where she used the hose, and it became much faster. It was a continuous because she was using the hose to take the water out. So continuous and discrete, it's important to think about the movement. If there's any movement, it's almost always going to be continuous, but if it's a one-time event like taking water out with the bucket, then that's going to be discrete. All right. X-intercepts and Y-intercepts. Now, we've spent some time with X-intercepts and Y-intercepts, and you should feel very confident with that. If you're looking at a graph, you should be able to quickly and easily tell me what the x-intercepts and the y-intercepts are. So if we have our graph and it crosses right there, then our x-intercept is going to be right there, and our y-intercept is going to be right there. And we always write our x and y-intercepts as points. So the x-intercept, y is 0, so we always put 0 in place of y. And the x looks like it lands probably at 3/4, okay? So 3/4 0. And our y-intercept Looks like it lands, I did a terrible job of, didn't do this really very well. We'll say that our y-intercept, we'll say that that's a 1 and that's a 2, is crosses at 0, x is 0, and y is 2. So it's important to know where a graph crosses the x-axis, and remember y is always 0 when it crosses the x-axis, and where it crosses the y-intercept, and that's when x is 0. And that's true of an exponential function as well. So I don't think I need to draw that, but you can look and see. But one thing that's interesting about an exponential function is that, and this time I'm going to do a little bit better here, is that exponential functions have something called an asymptote. An asymptote. Now, an asymptote, if you have an exponential function, let's go ahead and have it, we're going to have it start at 2, and we're going to have it come down and then get very, 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 very close to 0, but it's never going to touch 0. And an asymptote basically says, what's the line that the function comes very close to, but never, ever, ever reaches it. In this case, it's x is 0. Okay, x is 0. In another case, an asymptote might look like this. It might start at 0 and go up like this. And actually this isn't x is 0, this is y is 0, sorry. Change that to y is 0, okay, or the x-axis, okay. In this situation though, in this other one, the asymptote is right here. And its x is 2, okay. So there's usually a line that the exponential function approaches but never gets to. Never gets to. All right? So that's just a quick review of our different key features. There are actually more, but we'll have individual videos for those just because they're a little bit newer and not as much of a review. So let's go ahead and do an example. Let's look at this example over here on the left-hand side. It says, a taxi company in Atlanta charges $2.75 per ride plus $1.50 for every mile driven. Determine the key features of the function. Now we're going to go ahead and think about how to write this out and how we could graph this. So let's think about, if I was going to write this, I think I might say y equals, which is the cost of the ride is equal to $1.50 times the number of miles, x being the number of miles, plus the $2.75 just to get in the cab. Okay, so right away you can probably see that this is an exponential function, but let's go ahead and graph it anyway. So let's say that this is a half, and that's 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, 5. Okay, so if we're going to start, our y-intercept is 2.75. So that's 1, 1, 2.5, maybe right there. So let me get a different color. Let's see, I've been using purple for my linear functions, so I'll make that be my y-intercept, okay? So when you just get in the cab, you're charged $2.75. And then what happens if you go, let's go ahead and put my miles down here. This would be 1 mile, 2 miles, 3 miles, 4 miles, 5 miles, 6 miles. So if I go 1 mile, then I'm going to go up 1.5. So that's 1.5 and over 1. And if I go 2 miles, I go, let's see, I didn't do a very good job on that one, but let's see, there's 1. Let's see here. Make sure I did this right. So here's 1. No, that's a half, and that's 1, and that's the other half right there. So actually it's right there. Now I erased my blue. Okay, so this is a half, and that's another half, and that's another half. So that's 1.5. Okay, so I think I'm going to go ahead and just draw my line here. Now I'm not going to go below 0 because you never owe the cab. I mean, the cab driver never owes you money. So let's go ahead and connect my 2 dots. Okay. Now, question. Is this linear or exponential? Is it linear or exponential? Well, I think you can tell right away that it's linear, right? So this one is linear. Is it increasing or decreasing? Well, as my x's, as I read from left to right, my y values go up, so it's increasing. Where is it positive? Where is my line positive? Well, my line is positive when my y values are positive when x is greater than 0, right? Because this is where I started. X is 0 here. 2.75 is y. So anything beyond that, it's positive. When is y negative? Well, y is never negative, is it? Because we never go past this starting point of 2.75, okay? We're never going to get down here. Now, is it continuous or is it discrete? Well, this one's pretty continuous. It's continuous because you can stop after, a half a mile, a quarter of a mile. There's lots of different places. All these points can be included, okay? What are the x-intercepts? What are the x-intercepts? Well, are there any x-intercepts? No, the graph never makes it down to the x-axis, so there are none. I'll just put a null set, none. What is the y-intercept? Well, the y-intercept is where x is 0, and that's at 2.75. Is there an asymptote? No asymptote. Asymptotes are only for exponential functions, not linear functions. All right? So we have just described this function. All right? We've just described it. We've said that it's a linear function, it's increasing, it's positive when x is greater than 0, it's never negative, it's continuous, there are no x-intercepts, and the y-intercept is at 0 to 0, 2.75, and there are no asymptotes. Let's take a look at another one. Here, this one says a pendulum swings to 90% of its height on each swing and starts at a height of 80 centimeters. So a pendulum swings to 90% of its height on each swing. So if you think about a pendulum looks like this, right? You have something that comes down and it goes woo, and it swings back and forth, just like that, okay? Always 90% of its height. Okay, and the height of the pendulum in centimeters y is recorded after x number of swings. Describe the key features of this function. All right, so let's start by first saying that x are our swings, the number of swings, and the height is our y, okay? Now this time, instead of drawing a graph, I'm just going to go ahead and start with a table. So at 0 swings, we know that the height is 80. At 1 swing, we know that the height is 90% of 80. 90% of 80. So what's 90% of 80? Go ahead and figure that out. Did you figure out that it's 72? Now, feel free to use your calculator. Don't ever feel like you can't use a calculator, and I'm going to pull mine up as well in just a moment. Now, at the second swing, it has to be 90% of 72. So go ahead and figure out what 90% of 72 is. So all you needed to do was take 72 and multiply it by 0.9. And that gives you 64.8. Go ahead and figure out what 90% of 63 is as well. Go ahead and do that one. Did you find out that it's 58.32? Now, how are we going to figure out what 90% of, how are we going to figure out what the fifth swing is? Because we just missed the fourth swing. The fourth swing isn't listed here. So how are we going to figure out what the fifth swing is? Well, are you remembering the formula for an exponential function? If you have been remembering it, then that's going to help you, because as you look ahead, you're going to see we're going to have to figure out what the height is on the 10th swing, what the height is on the 20th swing, what the height is on the 40th swing, and the height is on the 80th swing. And I don't know about you, but I don't want to sit here and do each swing individually and multiply by 90%. I want to be able to use a formula. So let's see if we can remember. So the height is y, and it's equal to whatever our starting point is, which is 80, right? And what have we been doing? We've been multiplying it by 90%, or by 0.9, right? We've been multiplying it by 0.9. And we've been multiplying each time by 0.9. So how many times do we multiply by 0.9? Well, we multiply by 0.9 when we got 72, we multiplied by 0.9 once. On our second swing, we multiplied by 0.9 twice. On our third swing, we multiplied by 0.9 3 times. So that means we're going to multiply x times. We're going to multiply it to the x power. So now I can easily figure this out by simply using my calculator. So go ahead and tell me what the fifth swing would be. And now that you've done it, I'm going to do it. Actually, let me do it this way. I'm going to do 0.9 x to the y, and I'm going to say to the fifth power is 0.590, and I'm going to multiply that by 80. And that tells me 47.23. 47.23. Now that we know how to do that, why don't you go ahead and fill in the rest of the table? Fill in the rest of the table. Figure out what 10, 20, 40, and 80 is. Okay, so what did you come up with? You've got, hopefully you came up with something close to what I have. I did some rounding. This one actually probably should have been a 4 right here. But regardless, you should be pretty close to my numbers as well. Now, we've done some work, and now we can actually describe our function. So let's start by deciding, is it linear or is it exponential? Now, I'm going to use a different color because I want us to be able to tell right away when we look at these. So I'm going to use this bright green. Is it linear or exponential? It is exponential, right? Oh, that's not going to work. Let's use a darker green. It's exponential. Exponential. This is an exponential function. We can tell by looking at our graph that there is not a constant rate of change. Instead, we know that we are multiplying by 0.9, and that's our change factor, 0.9. And so that should be our key to tell us that this is not linear, it is exponential. All right? Is it increasing or decreasing? Well, let's think about if we were reading it or if we were graphing it. We would have 0 at 80, and then 1 is 72. And so as we're reading left to right, we're going 0, 1, 2, 3, 5. So our x's are increasing, right? But what is happening to our y's? Our y's are decreasing. They're getting smaller. So this is a decreasing function. Where is this graph positive? Where is y positive? Well, y is positive. Let's see. It pretty much is staying positive the whole time, isn't it? It's not hitting the negatives. And I think if you realize as we continue to take 90%, even of 0.02, it's just going to get smaller and smaller and smaller, but it's never going to cross that x-axis. It's always going to be positive. So y is positive. When x is greater than 0, just like our linear equation. And you can see that when you look at our graph. Actually it's when x is equal to 0 even, right? Y is positive. Y is at 80 when x is equal to 0, but it's actually when x is greater than or equal to 0, okay? All right, and then let's take a look. Is it ever negative? It's never going to be negative. Think about it. Think about this. At 80 swings, it's at 0.02 centimeters. If we take 90% of that, it's going to get smaller and smaller and smaller, but it will never, ever become negative. So it's never, never negative. So this one again is never negative, just like our linear was. Is it continuous or is it discrete? Well, that pendulum is swinging, isn't it? It's actually swinging. So it's going to be considered continuous because there is movement. It's not like it gets picked up and moved to the next spot. It's as it's swinging, it's getting to 80%. All right, so it's continuous. What are the x-intercepts? What are the x-intercepts? That means when y is 0. Well, let's look and see. Do you think we'll ever get the height to be 0? Will we ever get the height to be 0? No, we won't. There are no x-intercepts. There are no x-intercepts, okay? And what are the y-intercepts? Well, the y-intercept is when x is 0, and we can see it right here. X is 0, y is 80. So our y-intercepts are 0, 80. Okay? But in this situation, it's never going to hit the x-axis. Now, what is the asymptote? What is the asymptote? Well, the asymptote is going to be the line that the function approaches but never hits, and that is x equals 0, where actually y equals 0, right? Think about this here. It's going to start at 80 and it's going to come down and it's going to get closer and closer and closer and closer to y equals 0 right here, the x-axis, but it never hits it. So the asymptote is y equals 0. Ignore that right there. And that is describing functions using key features. All right? Make sure that you write a key idea. Think about some of the new things that you learned. Think about what is important to be looking at when you are describing a function. These are some of the key features. We'll add more in the coming clues. And go ahead and write your key idea, and I will see you in class.